So we will start with our yesterday's discussion on oscillators and any questions for that. Okay, so let me, there was one oscillator which we were discussing and I left it yesterday. So let me just point that. So we have a cell, a simple cell for an oscillator. So RC in and out. So this is input and this is output. So let me just model this cell so that it becomes easier a little bit to use. This is in and out. Okay. So what I told yesterday that if I have three cells, such cells in feedback, and I can satisfy the condition on the gain and phase, this is going to oscillate. Okay. And we also saw that if you start from time t instant equals to 0, you see that it is in a state where it can oscillate if the gains are proper. But at the same time, I also told that if you are trying something as pseudo differential, so in both these cases, I am maintaining that I can maintain a linear gain on both on all the cells. Okay, so the linearity still holds, and okay, so let me just. So I said if you have this kind of cell, then this is one of the pseudo differential oscillator, and if you are just having this thing in the system, this is not going to oscillate. Okay, because in looking at it, you can also find a stable point of means a stable state which is not an oscillation state, oscillatory state in this case. Okay, even when the nodes are pulled to VDD and ground. So then I told that you can make it oscillate if you have a cross couple inverters connected back to back on both of these nodes, and what this is doing is this is enforcing a relationship between two nodes, which is like writing it's like A is C complementary and B is D complementary. This is like what I can enforce. Okay. So in all the pseudo differential cells, you need to do something similar to this, may or may not be exactly this, but you need to enforce the differential nature in the two loops. Means two loops here you see. Okay, this is only a single loop. So let me just say which is the single loop you have. If you see, okay. So so this is actually only a single loop with 4 cells. Okay, and if you take, if now since we are using this particular cell as a basic cell where transistors are in saturation and your gain is GMV input GMV in into the load impedance. So in this case, so this was a, so let me say, if you do not consider any inverters in the system, any cross couple inverters in the system, you have means the gain as we worked out yesterday. If the gain of each is A naught by minus 1 plus S by omega P, this is gain of each cell. So this one, this gain will be minus 180 degrees, not minus 180. This is like you have A naught 4, and then this will go down as minus 80 dB per decade, the loop gain. Okay, and the phase response of this, so it starts from 0, and at omega tends to infinity it goes to, so let me just mark the x-axis also here. Okay, so this is omega p. So it starts from 0, angle of loop gain, okay, and it goes to minus 360 degree at omega tends to infinity. So let me just make it at 180, 270, and 360, right? So what will be the phase at omega p? It will be minus 180. 45-degree contribution from each. Something kind of this. So the valid question is, if you only have these four things connected in loop, then you do not have, means the frequency at which it will oscillate is infinity as per the Barkhausen criterion. So this is not going to oscillate. Okay. So now, okay, the two ways to look at it is when I put the cross-coupled inverters, what am I doing actually in the system from the loop gain point of view? So one thing, okay, you can look in two ways. One way is by putting so let me just write, with cross-coupled inverters, I actually enforce the relationship A equals to C bar and B equals to D bar. This is what I am trying to enforce. Okay, means this is just to look at a very top level picture that I am trying to enforce this relationship, and which helps me to understand that if this relationship is enforced, then this particular oscillator will oscillate. Okay, but this is still not talking of the Barkhausen criterion, but that has to be satisfied. So what else can you think what this inverter is doing? Now this 180 phase shift is a very direct, means how can you say that this is a 180-degree phase shift? Okay, negative GM block, you have to look between 2 points. Okay, you may not, you look at a differential then. Do not look at single ended. So if you just look at one block, so let me just plot the one. This is A, this is B, right? Now I'm just plotting it or drawing it such that you, so if I want to write a transfer function from VB to VA, which was earlier, so earlier it was only this old transfer function. Okay, now what can you think about, so all these are loaded, so B is also loaded, means B terminal is also loaded and D terminal is also loaded. Okay, so what can you say now, the addition to the transfer function? Pardon? It gives, you have a parallel path, so you are actually having two paths leading to the output, same output. You are actually, effectively you are adding a zero. So what that zero value will be right now, I'm not commenting on that, but you add a zero in the path. Okay, maybe some gain factor also comes in. And whether that zero will be left half plane zero or right half plane zero, can you tell? Why? Why? That's the other thing. Because the first path is also an inversion, right? So this is a left half plane zero. Okay. Now this left half, which one? So the thing is, if the two paths, so let me just make it like this, A and B, and let's say another adding to this. Okay, so like H1 and H2. Okay, if from A terminal to B terminal you are having two paths, if both are in phase, then it will be left half plane zero. You can work this out. No. Both are in phase. H1 plus H2 equals not equals to zero. I'm not saying that. What do you mean by that? Why B has to be zero? Yeah, VB means VB has to be 0, okay? Okay. If they are in phase, okay, let me just, then good point. So if they are in phase, then they will be, so what you are saying is, let me say, H1 plus H2. Now this is very much dependent on the transfer function itself, right? So H1 plus H2 equals to 0 at a 0 frequency, right? So now pick up the some value. So this for an example, let's say this is 1, okay? And this will be, what shall I, means I have to have some frequency dependence here. So that frequency dependence, how would you like to have it? Let's say omega 1 by s, an integrator. Okay. So this, no, so now pole of the h1 here I am taking h1 equals to 1. So means it will come due to the both the transfer function, right? H1 numerator and denominator. It's not that only H1 will be contribute or only S2 will contribute. But this is a simple rule that you can remember. You can work it out this out that if both the input paths are contributing in the same phase, means positive or negative right now, then you will have a left half plane 0. If they are in opposite, then they are a left half plane 0. Sorry, opposite is a right half plane 0. Another example which I can show, I think this part you might get it. So everyone would have seen from V in to V out, right? Okay. And then there is a CGD sitting here. And you know that this is a left half plane, right half plane 0 because of the CGD. You know that, right? Or no? So now look, from V in, because of the GM path, you are reducing this potential. But because of, if you increase V in, you will increase this thing due to CGD. They are opposite. And this is an example I can give. Means the other thing is you can always work out all the equations, but I do not want to work out all the equation. I am giving you a simpler version. Okay, so effectively this inverter is adding a feed forward path or any additional 0, which now depending on where this 0 occurs. So if I pick, let's say, a 0 position here, and whether all the zeros will occur in the same position, you can work that out. This will actually change the phase. Now, and depending on where it changes the phase, in the end, let's say if there are 4 zeros in this whole loop, then that should effectively become something this only, or it's all the way. It means I can have a different thing either. It depends. Okay, and you have a chance of, now whether you will cross this 0 or not, that very much depends what is the gain, where is the 0. Okay, so the gain of this inverter is very important. What is the gain of this inverter? G of both of these. So you can say if G tends to 0, if the gain is 0, then you do not see any 0, you at the same. But if G tends to be very large, maybe you are having a 0 at much away, so you may not cross, or you cross at a different frequency, where the gain, you may not have the gain equal to 1. But this 0 comes in, is beneficial for you to make it oscillate as such. Okay. So since we have talked that in differential, pseudo differential ring oscillators, you need to have this cross coupled inverters which adds a 0. So it is doing two things. It's adding a 0 and it is maintaining the phase relationship 0 and 180 degree. Both are important. Okay, so let me then ask one question here. So let's say earlier you saw that I was using 2, so it was little bit difficult to see that it can oscillate that, sorry, it was difficult to make it oscillate without having a cross couple inverters as such. Okay, so let me say I increase the number of the same cells to 4. Okay, and now same cross coupling I will have. Okay, yeah. Yeah, means it will. So single inverters means you can try it out. What, how many zeros does it have? Because if you are having single inverters, you will not have the same transfer function from one input to the output of each cell. Your transfer function will change. You got that thing. So the placement of zero right now, when I have these two cross couple inverters, I can write the same transfer function at for each input to the output. This is identical. No, no, no. So that's what I am saying. That one side also, when the transfer function from A to B will be then different from C to D. It is not symmetric. Okay. Then you work out the transfer function whether it is able to do it or not. Right now, I can just say that it is symmetrical to all. Whatever transfer function I find for one, it will be applicable for all. Okay. So now the question is, now I am having 4. So after 2 thing, now I'm having 4. Will it oscillate? So the thing is, if you can maintain somehow that this is always like complementary. So let me just make it this. This is A, B, C, D. A bar, B bar means if I can enforce these two relationships, then it is going to oscillate. Now here the phase, if you are looking at the phase, you can have a 360-degree crossing at some frequency. Okay. So the problem, because for the previous one doesn't seem to exist here. But who is there to enforce the relationship that you always have a complementary, means A and A bar are complementary once you start. So that can easily be enforced if I do the same thing. And I do it to have a symmetry, I do it for all. So let me just mark this. I pardon? Then it will not oscillate. Means that the frequency at which you will oscillate. Okay, so sorry to say, means if you starting when you are starting this, the phase relationship, if it gives you the at some phase 360 degree or 0, then it is going to oscillate. Okay, in the case of 4. But when you are trying to start the oscillations, let me just say at t equals to 0, you will have a steady state in this case where like VDD 0, VDD 0 and all, where it will not start at all. So in order to start the oscillator, you need to have something where you start in an opposite phase. Okay. So A and A bar should be in the steady state. Pardon? Yeah. Right. No, right? They will be the same. They will be opposite phase. So if you look, right, you are having a 360-degree phase across 8. So what will be across 4? 180 degree. So you can get that steady state. Okay. So the thing is, it might be slightly off, or it is not moving. It may not be as perfect 180-degree. Might be some away depending on gains and other, like gain of one with respect to the other. There will be a difference in the gain somewhat. So that when you put a cross couple inverter, that enforces that thing. Okay. Even when you put a cross couple inverter, in case of the even state thing, you can always have a metastable state where it doesn't oscillate at all. Okay, yeah. So now the question is, this is so. What are the drawbacks of putting your inverter? Let me just say here. Drawbacks of cross couple inverter. Okay. So one thing is your frequency of oscillation is surely lowered. And you can look at it in two different ways, that you are adding a loading to the oscillator, a capacitive loading. So for the same supply, your delay have increased, so your frequency of oscillation will go down. Okay, and the other thing is that means okay. So the thing is, the loading is the bigger problem here, and if you are so one thing is you might be fighting with the so let me just put it this way. So if this terminal goes high, you want this to go low. Okay, at that time this has to go low. Okay, and this goes high, right? But the signal coming from this is delayed as what would be coming from here. So you will be fighting against the means there is some other circuit block which is resisting you to make the change. With delay, it will come, it will assist in both the ways, but there is a added delay. So frequency of oscillation actually goes down. In addition to what loading have you introduced? Okay. The other thing, does that clear that when you put these cross couple inverters, it does that part. Okay. The other thing is all these inverters are working between VDD and ground. Means if I am using this, so then I have VDD and ground both on both the cases. So okay, let me just put it better. So VDD, ground, and so this is also VDD and ground. So actually your power consumption for the same frequency of oscillation increases. Power which is consumed in this increases. Okay. So what is the other way we can have a differential operation without having a lesser power consumption? Doing something similar what we are doing right now here. Hmm? Can you just repeat that? Uh-huh. True differential stages will have more power consumption maybe. True differential stages may not have. So right now we are still seeing this as a GM cell, or this is a transistor which is working in saturation. But soon we will see these are all the inverters to get a higher swing. And true differential stages can only give you a limited swing. So right now that is not the. We will see that you can do that part. Huh? Yeah, odd number of stages will not give you the even phases which you normally require IQ and their derivatives. So if I ask you think of like by putting these inverters, you introduced a zero in the system. What is the other way you can introduce a zero in the system? I'm just asking a way to introduce a zero from one node to the other. Hmm? Series RC will be a little bit any C you are putting your any R and C you are putting you are loading. So whenever you are loading, you can think that you are reducing the frequency of oscillation. Okay, so let's not put any. Means ideally, what do we want? Let me just put it this way. Ideally, we want. Let's say if I take this node and we know that C and C and the bottom one is complementary. I can do this, right? Gain block. The gain block which doesn't consume any power, which feed forwards the signal. Okay, and the simplest one would be this. It adds a zero in the path. Okay, and it helps in maintaining the relationship 0 and 180 A and A bar. Okay, so the thing is, if you make this, and the problem of this thing is also there, if you make the resistance too small, that means you are just then it will reduce the frequency of oscillation. And if you make the resistance too large, then you cannot maintain the differential operation. So there is some fine, like optimum value where you can have the maximum frequency of oscillation with a definite resistor. And the power consumption for this will surely be lesser than for the case of inverter. Okay. And why can't I do the same thing for this one? Means this is the bigger problem for we need to have zeros in the oscillator. Why can't I do the same thing here? So let me just put a resistor. Putting a resistor between B and D is effectively doing this. Okay, whereas putting the resistor the other way is not the same. So what we can, if I just go and do the same thing, actually I haven't done any, just become a resistive divider as such. Okay, and it doesn't enforce that 0-180 degree relationship. You can try it out. What zero does it introduce, or what does it do with the resistor in place? So here you need to have the, means for a two-stage one you need to have cross-coupled inverters. Whereas for four stages, more than two, for even stages, you can use a resistor which is much more power efficient. Okay, so yeah. What is the require apart from getting more number of stages? Yeah, you need. So the thing is, let me put it this way: if you need only IQ phases, and the power is the number which you are also looking for. Okay, so if the power which you are going to spend in the inverters, so you could look at two ways. One is if I need more phases, I have to go for four, no other choice. The other one is if I need only four phases, can I get it from only these four in the chain or eight in the chain? I have to do the whole power versus noise analysis, and it may happen that the power which you are dissipating in these inverters, if you dissipate the same power in the oscillator, can have a better phase noise. So the comparison should be done total power and the noise. Okay, so this concludes the part on the oscillations which we were looking at, single-handed and differential, and let's continue with the uh, what do you say, oscillator parameters, and that was the last where we left yesterday. Oscillator parameters and performance metrics. So I clubbed it together, metrics, and we talked about amplitude, in which case, in this case, it is limited by the VDD and the current, the frequency, which is dependent on RC. And we were looking at the linearity of the, if I look back yesterday's one, we were looking at the linear tuning range and tuning linearity. That was the one which we were considering. Okay. So 24th, right, sorry. Okay. So the other one, the points you're looking was tuning range and tuning linearity. And the conclusion was that ideally you want a large, ideally you want a large tuning range and linear KVCO, which is like the linear throughout for the linear loop dynamics of the PLL. Okay, so and whichever VCO you are making, basically designing, you have to evaluate what is the tuning range and what is the linear range of the KVCO. And we have seen that with the change in the KVCO, you vary the bandwidth and the phase margin of the PLL if you do not track it properly. Okay. The third parameter which is important in VCOs is your power supply rejection ratio. Okay, which is termed as PSRR, and this is very important because, so let's say you are having a VCO and all the power it is driving from VDD, and this is the output. So whatever noise you are seeing on the VDD, if that noise comes amplified or in whichever way at the output, and that noise actually changes the performance metrics in terms of jitter, means it actually, the noise on the VDD changes the output jitter, and which is sometimes it is not that acceptable. And why this can happen, you can say a VCO is a clock source, and the clock is used at many other digital logic in and around around the VCO, and they will cause a supply noise. And if you share the same supply with the VCO, so let's say I am having a big digital logic, okay, and this clock is going to the digital logic, and the digital logic, so let me just mark the clock a little bit better. So let's say this clock is going to the digital logic, and I am sharing the same supply with the digital logic. And you know, digital logic clocks every means it is a clock circuit. So if the CMOS logic, you will see a large glitches as per the clock frequency. Okay, and that noise can travel back to the supply of the VCO, which will change the timing. So which can change the timing. So the PSRR is a measure of how much noise is there on the supply and how much does it cause at the change in the timing jitter at the output of the VCO. So we have to take care of this, and we have to take care of this thing for a simple single cell, single oscillator also, and when you are using this oscillator in case of other circuits nearby. This becomes also quite important when you are having multiple PLLs on the chip, multiple PLLs and oscillators on the chip. Like, so it's like I can have a different, so let me just give another example, that I can have multiple PLL, PLL1, PLL2 for different digital logic. This is very common these days, all in your ASICs. You have multiple PLLs for different applications. So whatever is, so you can say if both of these are existing in the same chip, any noise, supply noise, which is picked up due to one PLL to the other, that has to be rejected at the output. Means this should be clean, otherwise you will have more jitter, which is again like which worsen the performance. So PSRR is a measure of the power supply rejection, and there are circuits which are designed to reduce the jitter contribution. We will look at that. So that is one performance matrix. The other one, as usual, we all want low power and low jitter. So power and jitter. Power and phase noise, let me put it this way. Ideal requirement is lowest power. These are ideal, we can never get that. Lowest power and low phase noise. These are always designer's choice. Whenever you go and design any oscillator, you would like to have the lowest power with the best phase noise. 6 you can have. Okay, so these are the performance metrics, and now we will see how the different kinds of oscillator cells are performing on different parameters. Okay, so the first one which we have seen, so the amplitude and frequency, you know, so amplitude is here defined by your VDD and I. So let's start with the cell which we had. So R and C, this is a single cell, input and output. Here omega P is equals to 1 over RC, and whatever is the bias current, based on the bias current you will have the output amplitude, GMV in R. Okay, that will be the amplitude. So in this case, this particular case, you cannot switch off the current source completely, right? Because you otherwise all your linear gain and everything is off the hook. So if you want to have this oscillation frequency omega p equals to 1 by RC, you are operating this transistor in a saturation region, and the swing is limited by GM, the gain GMRO. Okay, so as R and C vary, your oscillation frequencies vary. So one thing is, if R and C varies by plus minus 20%, then your oscillation frequency varies, which implies omega oscillation vary. This is another part, means this is the byproduct of the process variation. But if I just turn back the question, I say I want to vary oscillation frequency. Vary oscillation frequency. What shall I do? If that is the requirement. Change RNC. Means at one time I was seeing as a bad thing, now I need a knob to vary the frequency because I need a tuning range. So want to vary oscillation frequency, I can vary R and C. Now, how do you vary R and C as such? So let's say I have, so let me pick up with C as such. So this is plus minus VC. So the normal way to vary the C would be, if you are realizing this C with a with metal plate capacitance, then you will have some kind of switches connected to C. So this is X, 2X, let me just put it as 2C, and so on. So I can have a capacitor bank to vary the C. So if this is variable, this is one way to vary capacitor bank. Okay, but as soon as I say this is a capacitor bank, you have to control this digitally. So that somewhere the PLL has to convert this analog output to a digital to control this capacitor bank. That is one. Other way you can vary the capacitor if you are using so which other way can you, so either you can use a MOS capacitance and change the gate voltage if possible. That is not that much done in case of oscillators. Okay, so that is one way. So I can use MOS capacitance, that is use MOS capacitance and vary VGS, right? So what I am saying is you can vary this voltage plus minus VC. Okay. The other thing to change is R, and the way you can vary this R is again you can use a resistive bank. So with a switch, so this is resistive bank, resistor bank, and you can again, if you are using this, you need a digital control. So you can use, the other thing is to use a MOS resistance. So since we are using this R at the connected to supply, let me say I'm using a PMOS, this is VDD, this is your output terminal here, and this is V control. Okay. So I can use the MOS resistance to control the oscillation frequency. So let's see what happens if you try to do these things. So let me pick up with the MOS resistance at the oscillation frequency. Now the thing is, I will switch from your single-ended delay cells to a differential delay cell, so that you do not see the problem of current source going into a triode region depending on. So the thing is, we are trying to get certain swing. Okay, if I keep using a single-ended one, then it becomes important what is the VDS of this transistor. Okay, so right now I want to avoid that. I will switch to a differential cell. You can do the same thing. The only thing is the analysis gets a little bit difficult. So the current cell which I was using earlier, now this is the current I naught, your VIP, VIN, and this is the PMOS. The outputs are still loaded with the same cap C, and this is VOP. So let me just write it as plus minus V out. This is V control and VDD. Okay, and effectively what I want that this MOS given at V control should be behaving like a resistance whatever I want for a desired frequency R on. So in this case, and these VIP and VIN are acting as a switch, changing the current, switching the current from one side to the other. So here R on is equal to your, so let me write it as, the one thing which you need to ensure is that both these transistors which I'm using as a resistor, they should be operating in a linear region. Okay. Now all these things will come into existence because you are trying to change the frequency by varying R. The benefit which you can see is that this seems to be an analog control which can directly come from the loop filter output voltage. It's an analog. Okay. So I is kW by L into, and all the assumptions right now I'm making that VSG minus mod VTH minus V control times VST minus VST square by 2. Okay, so R on is effectively equals to kW by L into VSG minus VTH minus V control, neglecting the second order term. So now your oscillation frequency is inversely proportional to our RC. Here R on C, let me just write it as R on C, which is equal to your kW by L into VSG minus VTH minus V control by C. Pardon? Oh, I wrote it. So let me just, sorry, write it as VDD. That makes right? Yeah, you are right here. So this is VDD. Okay. So you are having your frequency of oscillation as directly proportional to V control. Okay. Now this is the frequency. Now what is the amplitude? So the output different, if I am plotting VOP minus VON, it will be something like this. Okay, all these things symmetric and all that all depends on the switching. So this one is VDD and this will be VDD minus I times R on. Okay, I think this is simple switching of the, pardon? What is it then? So that's why the proportionality constant can be minus, right? So proportional in the sense you are seeing a proportional, if V control increase or decrease, a linear change. Okay, so it is in that sense. So now here amplitude of oscillation is I times R on, okay, which is your kW by L into VDD minus mod VTH minus V control. Okay. So, and let me just write it. In all these cases, let me make this transistors M1 and M1 dash. M1 and M1 dash have to be maintained are in linear region of operation. Because once they change, then you will have a different R on. Okay. So what happens if they become current source? Okay, let's pick up on that. Pardon? Why do you think a delay? Yeah. You say, no, when you're calculating the delay, where are you calculating the delay from? If this becomes a current source, let me say, no. So when I am saying this is in saturation, I am saying this is in saturation all the time. Okay. I'm not saying that it goes from linear to saturation region. That's a different case. That we will deal it a little bit later. But if this becomes a current source, your V control is like that it becomes a current source. In that case, what will be VOP and VON? You can't comment on that. You are having two current sources, top and bottom, and nothing controlling in between, right? So it can switch to one side. depending on the current. Means in a practical sense, either this node is going to be VDD if the current is so small, or if the current is so large, then it will basically pull down to zero, and even the current source will get crushed. So maintaining this with the swing, maintaining this in a linear region in the presence of a swing is important. So let me say for a given MOSFET, this is V control VDD, and this potential is okay. You can find this thing. So if it is VDD minus I times R on, okay, R on itself is dependent on KW by L and every other thing. This should be in a linear region, that is VDD minus V control minus mod VTH is greater than your I times R on. You need to maintain that. Okay. And if I change my I, effectively my I don't know, if you change control, things change here, both the F oscillation and the amplitude. Okay, so another thing which you see, in order to have a larger oscillation, you see that here the frequency of the oscillation and the amplitude of the oscillation both are changing with V control. Okay, and if you are using this particular kind of cell, which is supposed to give the clock to the following blocks or any blocks which you are used, you only want to change the frequency, not the amplitude. That is normally the digital logic will work on. Okay, so your amplitude should be independent of your oscillation frequency as such. Okay, and here if I just one remark here, that if I want to have a larger oscillation frequency, I need to have a lesser V control, right, as per the equation which is coming here. So it's a negative. You need to take this into account when you are making the whole PLL loop. So one thing is, when you are making any VCO, you should check for the, so let's say for any V control to frequency which you are looking at, okay, you should see whether this gain is positive or this gain is negative. If you do not take this into account and you just close the loop, the PLL may not work at all. And this is very important. Sometimes it is positive, sometimes it is negative, depending on how you control it. Okay, so let's stop here. We will continue with the oscillator tomorrow or Monday actually. Okay.